Good day, I'm Dr. T, and welcome to my office. Today I'd like to talk a bit about molecular orbitals. So we've talked about hybrid orbitals, the idea of taking s and p orbitals, blending them together, because the strictest sense of an s and p orbital only applies when there's nothing else going on. In this case, we've got some covalent bonding, so there's definitely some other things going on. In that case, we only talked about the orbitals for the valence shell. However, there's more orbitals in an atom than just those in the valence shell, and the hybridization actually goes a good deal further than simply what we talked about earlier. Typically, molecules will start forming what we call molecular orbitals, and these are hybridized orbitals for all of the orbitals within the atom. Typically speaking, similar shelled orbitals will start pairing together. So the 1s of one atom and the next 1s of the next atom over will start forming a molecular orbital. And I'll have a diagram pop up probably over in here with a couple of examples of this. The idea here is that we start out in this diagram showing the molecular orbitals in the middle and the originating atomic orbitals on the sides. Now you'll notice whenever you see these are usually for molecules that are only comprised of maybe 2 or 3 atoms. This is a case where complexity goes up quick with scaling. And so beyond more than a couple of atoms, the math starts to require a computer to start sorting out. Actually, it's a bit of a pain even with just 2 atoms. So we're not going to deal with the math here. I just want to introduce the idea that's taking place and a few features to this. For starters, you'll notice that you're forming bonds. Some of these in these diagrams will have a star. These are called antibonding orbitals. So a molecular orbital can be bonding. In that case, the electrons are predominantly hanging out between the nucleuses, and they're holding the 2 nucleuses together. Alternatively, they can be antibonding. They're typically going to be away from the nucleuses, and they're going to be allowing the nucleuses to pull apart. So if I see a bunch of bonding and antibonding orbitals, then my total number of bonds is going to be the difference between them. So bonding minus antibonding. If you were to try and do a molecular orbital of, say, Ne2, what you would find is there would be an equal number of bonding and antibonding orbitals. And that's not surprising since there is no neon. Instead, you just have neon atoms all by themselves. Because if they were to try and form molecular orbitals, they would all cancel each other out in having both an even blend of bonding and antibonding. Now, a few more features start popping up when we're starting to look at these orbitals. For starters, in some cases, you get unpaired electrons when you would expect to have pairs. So when you draw something like O2 and draw a Lewis structure, all of the electrons are paired. But in reality, when you look at the molecular orbital diagrams, and these do tend to more closely resemble reality than the other models, the classic trade-off, it's closer, but it's a lot more work. What you'll find is that diatomic oxygen has 2 unpaired electrons. They're in 2 different orbitals. This actually explains a lot of the interesting quirks of oxygen. For starters, oxygen is fairly reactive, which wouldn't be expected for a traditional double bond, but realizing that these are unpaired electrons, this starts to explain the fairly high reactivity of molecular oxygen. Yay! It also explains a rather interesting phenomenon. It's called paramagnetism. So when you have electrons, and if you have unpaired electrons, so that some are spinning in one direction and there's not enough spinning in the other direction to cancel them out, you actually gain a magnetic field around your molecule. So oxygen has 2 unpaired electrons that will typically spin in the same direction. This imparts what we call paramagnetism to oxygen, and oxygen will be attracted to a magnet. Now, I should point out this is a whole lot weaker than what we normally think of as magnetic. What we normally think of magnetic is called ferromagnetism, classically thought up as with iron, hence the ferro. In this case, you have many, many atoms, all with at least 1 unpaired electron that all manage to line their spins up together so that they add up the magnetic fields in this nice orderly fashion. When you form a magnet, you're actually in the process of lining up these magnetic fields. Some molecules and metals and other compounds will do this relatively readily, while others just won't. And even those who do this ferromagnetic approach, at enough heat, reaching what we call the Curie point, you'll break down the order no matter what. So you can always erase a magnet by warming it up a tad too hot. Now, if you have an equal blend of right and left-handed electrons, or I should say clockwise, counterclockwise, plus and minus, then you will reach a state what's known as diamagnetic. You have no net spin. Your spin adds to 0, and you'll be mildly repelled from a magnet. Molecular orbital theory has a couple of interesting applications. Well, generally we don't use it for size determination. It's that hybrid orbital theory does as good or a better job with a lot less work. Molecular orbital theory does work well for things like chemical reactivity, spectra, and determining which compounds are going to be conductive. A key to all of these points is the relationship between two molecular orbitals. Specifically, the molecular orbital that is the highest energy, yet still has electrons in it, what we call the highest occupied molecular orbital, or for short, HOMO. The other orbital of question is the one just above it, the lowest energy molecular orbital that doesn't have electrons in it, or the lowest unoccupied molecular orbital, LUMO. The HOMO-LUMO gap starts showing a lot of spectral characteristics, as the characteristic jump between those two can quite often be one of the most important spectral characteristics of your molecule. If you look at a lot of your dyes, they have a particularly useful jump between those two, and that's actually the color that they're absorbing, making it the dye of interest. So if they're, say, a red dye, they're probably having a corresponding, say, blue. Once again, good old-fashioned color wheel. It looks like the opposite of the color. With that said, have a wonderful day.